Okay, so page 14 there, guys. Now, what did we do in the last class? You remember? What did we do? So I think what would be good is if I ask people to give me some definitions from the last class. So, Jingdong, do you remember what strength means? Strength.
The force that defends the change of the shape.
Not quite this. Do you know, Leslie?
Definition?
Yeah, definition of strength.
Strength.
Yes.
Strength, like this, a circle thing.
No, not this one. No. Do you?
Stress.
Strength.
A strength.
Strength, yeah.
A strength.
Yes.
A strength.
Yeah, go on.
Yeah, like this, for example, a cup.
Yes.
Here is the strength.
Not this, no.
No.
Strength is, Mustafa?
Force required to break something.
Yeah, the force you need to break it. Okay. Now, Hussein, do you remember what ductility is?
Yeah, it's the condition you are able to get conduct. No, wait.
No.
It's the measure of how you can get shape.
No.
How easy
Yes,
change
yeah,
shape
yeah.
happens.
Ductility means if something's ductile, it means you can change its shape into what you want, without breaking it, something useful. What's the other one we have? Toughness. So who remembers toughness?
Doesn't crack.
Yeah, and then what was the other one we had? Let's see. We had also stiffness. What's stiffness?
It's the
Stiffness?
hard to change the shape.
Hard to change
The
the shape.
opposite of that too.
Yeah, pretty much, yeah. Now, what's the formula for Young's modulus? Stress over strain. And what's the formula for energy using stress and strain?
1/2 multiplied by.
Yeah, it's a half stress times strain.
Yeah.
That's for energy.
Yes.
Now, it's raining. Now, Jingdong, you remember this from last week. You drew us the diagram. What's grain boundaries?
Green boundary.
Mm.
Green boundary.
Oh, you drew us the picture, Jingdong. Oh my goodness. How could you forget? You drew us a beautiful picture.
Yes, I remember. It's some little.
What's called please?
Grain.
What's the name?
Grain
yes.
boundaries.
On which page is this?
31.
I'm sorry.
That's okay. Grain boundaries. Remember, it's when you make the shapes all different, so that it's difficult to. It makes it stronger. When you make all the shapes different, you know, like instead of being like all nice circles, you might have them all like different shapes, so it's hard to move them. Remember, you drew the picture for us.
You mean change the shape can change the force of the metal?
Yeah,
Okay.
yeah. And then we did metal fatigue. Leslie, do you remember metal fatigue?
Metal fatigue.
No, actually, I'll ask someone else. Ted, do you remember metal fatigue? Yes.
Yes.
Go on.
If a metal changes shape and return it back.
Yes.
Shape and return
Yes.
it will fatigue.
Yeah.
And
So
break.
yeah, very good. If you keep changing the shape and keep applying a force, you can break it this way. That's metal fatigue. And Albert, do you remember metal creep? Yeah. You remember now?
Melting the metal
Yeah.
to give a shape.
If the metal becomes hot, it starts to lose its shape. What was the example we had? Maybe the airplane.
No.
not glass. And then we have the fracture. So what was it? We had brittle fracture. What's brittle fracture? Brittle fracture is like with the window. Yeah, and then the other type of fracture we had was ductile fracture.
Yeah, the building.
The stone, the building, it's grows slowly. Do you remember the word propagate? What's propagate? Propagate means to spread out, to move out.
Oh yeah.
Mr. Steven, metal fatigue, that's.
Yeah, Ted gave us metal fatigue.
Make the metal weaker if you give a rest.
If you keep putting a force on it and giving it a rest like this, makes it weaker. So, for brittle fracture, it means the crack propagates quickly. And for ductile fracture, it means the crack propagates slowly. So what's an example of brittle fracture?
Ice.
Ice, glass, and ductile fracture?
Building.
I think wood, stone,
Building.
building, yeah, bricks. Yeah. Okay, good. And then we also had foreign atoms. Do you remember foreign atoms, Leslie?
Foreign atoms.
Foreign atoms.
Foreign atoms.
Yeah.
I know atoms.
You know atoms, good. Jing Dong, do you know foreign atoms?
Foreign atoms, just like
Yeah?
to combine. Oh, sorry.
Yeah, you're right, yeah, to combine.
Yes, such as there are 2 or 3 kinds of metals to combine them into one metals and get another fourth characteristics.
Yeah, so you're right. Foreign atoms is when you have something pure, like, what did we say, gold or what was the example we had last time? Iron, was it?
Maybe.
Yeah, bronze. What's bronze made of?
Iron, copper.
Iron and copper, isn't it? So you have something pure like iron, and then you add something,
In the main metal and
change the shape, change the structure, yeah.
yeah.
Good. Now look, you have the book here for this. After class you should read the chapter again to try and remember the words.
The whole chapter again?
Of course, this is what you need to do as a student.
And Mr. Stevens,
Yes.
if there are some definition question
In the exam.
Yes.
You'll get definition questions in the exam. So the question might be, what is the definition of stress? Or what is the definition of strain? Or what is the definition of strength?
Okay.
You know, so you do need the definitions, okay? Right, so we'll just go now to page, where are we? 14. So we're talking about structure of materials. Now,
There are gonna be questions?
questions? Of course. Yeah, of course. So if you can look, well, I won't actually spend too much time on this because you've done this with Lorraine. What are objects made of? What are the little things called?
Metal.
Atoms, yeah? You've done this with Lorraine. So someone give me a very simple atom.
Aluminum.
No, simple. It was the simplest one. Hydrogen. Hydrogen. So what's interesting about hydrogen? It's just one, what's this called?
One electron.
No, the electron will be outside. I'll put it here.
Nucleus. Proton.
Yeah.
Proton. And then here,
Electron.
electron.
And one proton is the same as one electron.
They must be the same. Why is this? Because the proton has a positive charge and the electron has negative charge. But I mean, you've done this with Lorraine, so there's no point in us spending a lot of time on this, but we just remind us of the vocabulary. So we have proton, electron, and this is an atom, and I won't spend any time on this, okay? You have these words. What words you should also have, okay.
Molecules.
Now, I don't know which one you use for Lorraine, so you can tell me which one. Atomic and molecular mass. Which one do you use? Or which one do you know?
Molecule mass or zero.
All of them.
Capacity.
Which one do you know?
Atomic number.
Oh.
Atomic number, very good. Okay, so we'll do atomic number first. So what is atomic number? We'll do that first.
The number of the proton and electron.
Yeah? Yeah. Atomic number. Atomic number. So what is it you said, Mustafa?
Number of electron and
Yeah. I think actually, more precisely, it's just the number of protons, but they should be the same.
electron.
Yeah. So what is it for hydrogen?
One.
1. That's the atomic number. Okay? And then what, here, I'll get some other examples here. Hydrogen is 1, helium is 2, lithium is 3, and so on. They're the atomic numbers, okay? So we'll do, I'll write a couple down for you. Hydrogen,
Just write the simple.
1. The spelling would be good for you to learn as well, right? Because I don't know, in the exam they could use the word, not the symbol. Helium is 2. This is actually on the bottom of page 16 if you're looking for it. And I'll do one more, lithium. Actually, lithium is a word you might recognise.
Yeah, new one. So
Where have you seen lithium in day-to-day life? Albert or Ted? This one here, lithium. Where would you see this in day-to-day life? No, wait. Ted will tell me. Where will you see lithium? Battery, very good, very good. And Albert, so you can have this for a battery. And Albert, helium, very good, balloon. And then hydrogen.
The air.
Yeah, give me an example where you would see hydrogen.
water.
Yeah, but just in pure form, pure hydrogen.
Flat ball.
No, nothing to this one.
Underwater water.
No, more day-to-day life, normal life. No. A car. There are some cars, I don't know if you know this, but there's some cars that use hydrogen.
Yeah.
So this day-to-day life, you can see these pure atoms, these pure materials. Yeah? Do you know Mark, the business teacher?
Yeah.
You know the business? You know him, yeah. Do you know the business teacher?
Yeah.
His wife has a shop that sells helium balloons. And actually he said helium is quite cheap. So if you have a tank of helium maybe this big and this wide, so only €300. I think that's a good price. So like this big and this wide, €300. So
Enough for how many balloons?
well, you have to ask Mark, but she makes a lot of balloons, so I don't know. No, I haven't done that. Have you done
Yeah,
that?
the song will change it, I don't know how.
Yeah, it's so weird.
Have you done it?
Yeah.
I
It's
didn't
like
try it.
You know what?
weird.
Maybe we can get a helium balloon off Mark and we can do something with it.
And Mr. Steve,
Yes.
what's blow mean?
Balloon.
Balloon! Ah, jing dong. This is a balloon.
We will go to McDonald's and you get one free.
Yeah. Yeah, for like there's a nice red balloon. You know this, and then like
What's balloon?
Yes.
Translation.
There's a goddamn king's extra.
Oh.
They're stealing.
balloon. You know this, right?
Can't
Just
you-
so that
Let me
side
translate.
fly ball.
No, flying ball. Yeah.
Let him translate.
No translations. Yeah.
If we have a 100 balloon and fill that, make us fly.
I think you need much more than 100, maybe 1,000,
1,000.
or maybe 10,000.
Maybe he watch an up movie.
Watching up, yeah. Okay, anyways, that's atomic number. All right. So next thing now I want to do with you. Oops.
Nice number.
Now, I want you to start to write some notes, okay? So,
I'm free. Avocado.
who's this?
Avocado.
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 And, no, and the name of his number is,
6.3.
no, the name, the letter. What letter do you use for Lorraine?
K.
Yeah, that's what I normally use. Now, in the physics book, they use L. I don't know. But I think we should use K. Do you just use K by itself? Just K like this?
No, scale K for Kelvin.
No, that's capital K. This is small k. What letter do you use for Ted?
Yes.
What letter do you use for Lorraine? For this?
What?
Okay, Albert. What letter do you use for Lorraine? You did this in Lorraine's class, didn't you? It's K, is it?
You won't find
There is one.
Well, anyways, what's the value of it?
6 point something multiplied 23.
Yeah, 6.02.
It's big L.
You use big L as well?
Yeah.
That's what I thought actually. Well, where do we use K then? Oh, K is Boltzmann's constant.
PL.
Yeah. That's Boltzmann. Sorry, yeah. L here.
It's the one that has the 8 value.
Yes.
10.
10 to the power of 23. And what's the unit here?
Joe.
No unit. It's just a number.
What?
Yeah, it's a number of things, yeah. Yes? Now, how do you use it? How do you use it?
By calculating.
Yeah, no, but what's the use for it?
To find the number of molecules.
Yeah, so
Number of
let's take for example, helium. We'll do helium. So how do you use this constant for helium? What way does it work?
By finding the mole of 1 mole of helium, then multiplying L's.
Yeah, it's a bit tricky. What's the atomic number for helium?
I don't know. I think it's 2.
It's 2. Okay. This is what you do. For helium, you say 2 grams of helium.
Yeah.
Yes. That will equal
1.
L, number of atoms of helium. Okay. So, for example, let's do hydrogen.
1.
So what's the atomic number for hydrogen? 1. So that means 1 gram of hydrogen, you'll have L number of atoms.
That's saying you're doing like
This one?
Yeah.
It means number. So for example, if I wanted 4 grams of, let's say, helium again. So there's helium. What's the atomic number of helium?
4 yeah.
No, what's the atomic number for helium?
2.
2. So 4 grams of helium equals 2 multiplied 2 grams. And this 2 here is the atomic number. So it equals 2L atoms.
How is that 2 multiplied 2 is 4?
Yeah, but you see what you do is you get the atomic number by itself, and that's, you need L.
You want to know what's you have to figure what's to L.
No, it's let's say the atomic number was 8 grams, or 8. Okay, so for example, oxygen. Oxygen has atomic number 8. So that means to have 8 grams of oxygen, you need 1 L of atoms.
Oh. Oh yeah.
You get the idea?
Yeah.
So if I want 16 grams of oxygen, how many atoms is that?
2.
2L.
Yeah.
16 divided by 8.
Yeah, like this too.
Yeah.
Yeah. So do you get how to use this?
Yeah.
Yes? Okay. So, where's the definition now? Okay, well actually maybe we'll look at an example here. But just before I give the example, I want everybody to try to summarize the definition of this constant. So did you all write down the value of it? And did you all write down how it works, how you use it? So what would be, well, I tell you what, you try to write the definition and then I'll ask you to check. So write down the definition and how to use this constant L. What's the value of it?
2.03.
6, wasn't it?
6.02 10 power 23.
So try to give me the definition of how of this and how to use it. Huh? Come on, snap to it.
From where we have to get? What should we do now?
Use your mind to write down a definition of what I just taught you. Because you need to practice making your own notes.
Here.
Yes.
The definition of L.
And how it works.
Okay.
Okay. So Jingdong, are you translating there?
No, I know it.
You know it? Perfect. Give us your definition, please. Don't be shy. Did you write it down?
No, I'm thinking.
Oh, get writing. Leslie, do you have a definition?
No.
No, okay. The same? Ah, guys, come on. We need to learn how to make definitions.
The number of atoms that you get from N over R.
Okay, you're good. You're getting close to it. I like this. Ted, do you have a definition?
No.
Albert, do you have a definition?
The number of particles in 1 mole.
Good, good. Okay. Right, look. Right. If something has an atomic mass of, let's say, X, this means it will contain L atoms in X grams.
So you have to get the number of atoms.
You have to get the number of atoms, yeah.
That's N equal G over MR.
If you want to write it like this, yeah. But I was looking at more.
What about 9?
Yeah, but I wanted more like a sentence, a paragraph. Now, what was the other thing I was saying? And then Albert, you used the word mole. So 1 mole equals, I think 1 mole, you could just say 1 mole equals L atoms, yeah?
Yeah.
Okay, so this is what I mean by definition. Something like this.
Contains L atoms
In X grams. Now, he also talks about a mass spectrometer. Where have you seen that before?
Yeah.
Yeah.
Where have you seen it?
No.
Chemistry. You did mass spectrometer with Lorraine in chemistry.
Just a piece of paper. That's all.
Yeah, but I mean, you've learned this word with Lorraine, yes?
Yeah.
So we won't do mass spectrometer because you did it with her.
Yeah.
What we'll do now, can I go to the next page?
Yeah.
Yes?
Just a minute.
Okay, come on, quickly. Okay. Now,
Sorry.
it's okay. Next page. Okay. I'll give you an example now. come on, listen. Let's see. Okay. This is some container, let's just say, of water. And let's see what we put into it. We'll put into it. Oh, it doesn't matter. You have inside it very, very small particles. Okay? And when you look at them very closely, they don't stay still. They kind of move around like this.
What about that?
Not quite this. So like here's your particle,
Free to move.
and it's in the water, and it moves like this maybe. It doesn't stay still.
Oh, you mean the lines is the particles, how it moves?
Yeah,
Okay.
and it moves like this. Okay? Do we know the name of this movement? I don't know. Did you do this with Lorraine? It's called Brownian Movement.
No.
No, you haven't done this. Okay. Anyways, why does it move like this? Why doesn't it stay still?
Because there is no electrons.
No. Why doesn't it stay still?
Because the water.
Yeah, it's something to do with the water or the air or the gas. What is it?
So what the atom of water and the atom of these.
Very good. So what happens is this. Here's your particle, and then you have the water or the gas or the air. It will hit it here. It'll hit it here. It'll hit it here, and bounces back. But maybe one doesn't hit it here. Maybe it misses like this. So which way will this move?
Right.
No. This one hits it. This one hits it. And this one hits it together. But this one misses it. Which way does it move? Down and...
Up.
No. I think it will move this way.
Which, you mean that atom?
This one.
What?
This one.
Yes.
How is that?
I think the opposite one.
Well, it'll move up.
Oh no, it's going the other, like a little.
Here, let me draw you another one. And make it very, 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 very simple. Here's our particle. And then one goes like this. And then one goes like this.
This table.
And then one goes like this. And so which way does this move?
Let's touch right. Just
Which way?
Right.
Left!
Why?
Is it like crashing and bouncing back?
Yeah.
Okay.
Look. Oh. Look. This one here has mass
okay, I
m
got you.
and velocity u. So it has momentum mu. And this one here has mass m and velocity, I'd say minus u, because it's the opposite of this one.
Yeah.
So this plus this is what?
0.
0. So nothing happens this way.
Yeah.
Now this momentum here goes to the left, and the momentum now is to the right. So you need to have some momentum to the left to cancel this. Remember, conservation of momentum. Yeah?
Then the first one goes the left upper.
So this one here goes left.
No, in the first.
I'll forget about the first one now. We'll just deal with this one.
Right. It just goes left.
If we want like the left equal right, left should
No. That's for force. We're doing momentum. Look. Let's say this is at rest. So what's its momentum? 0.
Yeah.
And its momentum here, let's say, is mu, whatever. Then afterwards, maybe its momentum would be minus a half mu. So its momentum is less, yes?
Okay.
So that means there's some momentum in this now. We put this on.
Yeah.
Look. 0, and let's just say -1, right?
Mm.
Then afterwards this will be x, and this will be, say, +0.5 meters, what's momentum? MV, meters per second newtons, isn't it? Or no, sorry, kg ms. Kg ms, okay. So what's the total momentum before? This plus this, which equals -1. And afterwards, x plus 0.5. And they must be equal. So what does x equal? Minus x plus 0.5 equals -1. So x equals -3/2. So that's to the left.
Minus half.
No, Mustafa.
Yeah, okay. Okay, I understand.
Okay. Now, if the particle is very big, okay, like this, it hits from all different directions. But suppose one is missing from here. It will go that way. But because this is so big and this is so small that you can barely see the V will be tiny. So you don't see it move. So you only have, where's the word gone? You only have Brownian movement when it's very small. Okay, please write a definition of Brownian movement, and I will ask you for it now.
How to spell brown?
Oh, Ching Tong. There.
B-R...
O-W-N-I-A-N.
Can you go back?
Yes, yes.
This movement is happening in a mass spectrometer, or is it something like completely different?
Huh? Say again?
This one is, does this happen in mass spectrometer? Is it?
You'll have to ask Lorraine for more information on the mass spectrometer.
No, I'm just like, is it like...
It tends to happen with particles that are sitting inside a liquid or a gas. So I don't really think that's the case for a mass spectrometer, is it?
Well, it's gas.
Maybe so. Ask Lorraine. Anyways, Ted, give me your definition.
I think it's due to the molecule surrounding
Yes?
surrounding the particle.
Very good, yes.
Bombarded.
Bombard.
Yes, bombard.
Very good. Go on. Yes, good.
Not equal.
What's not equal?
Unequal.
Come on. You're doing so well.
Unequal.
Ted, or Albert, try to help him. Finish his definition. So he said, Brownian motion is due to the bombardment of particles and...
Due to the irregular...
No, your definition. So Brownian motion is due to the bombardment of particles that are not, I see what you mean, not equal. Not, what word could we describe to mean it's not all the way around it? It's not constant around it. It's not consistent. It's not regular.
Not equilibrium.
Yeah, not an equilibrium, yeah. So basically one is missing, and then that makes it move a little bit.
I write a nuclear that get attacked from.
No, well, Ted had a better word than attack. What word did you use? Bombard. You did this with Lorraine. Yes.
Can you say the Brownian movement?
Yeah.
Is, is the movement needed by the pressure of other atoms.
Oh, very good. Yeah, you could say it's due to the imbalance of pressure.
Balance of pressure.
Yeah, that the balance, the pressure is not balanced.
Okay.
That there's one piece missing.
Okay.
Yeah. See, we have many definitions. Many definitions. Good. Okay. Next one now. Let's see. I'll give you an example. Okay. Now, copper has atomic mass or atomic number 64. And
Example.
yeah, and its density equals 9 grams per centimeter cubed.
What's now? Density.
Density, yeah. And the question is, what are we looking for? Yeah, we're looking for how big it is. Okay. Yeah, how big it is. Okay, so we do this together? So your copper is number 64 and its density is this, and we want to know how big it is. Okay, so maybe I'll draw it as a circle, I think, or a box, whatever. I don't really mind. Okay, here's our box. So our copper's inside it. Now, what does the 64 tell me? That if I have 64 grams, that will equal how much? How many atoms?
6.03.
02, yeah? Times 10 to the 23. That's how many I have in 64 grams.
Yeah.
Okay, so that is the mass. And we know the density, so we can get the volume. Yes? The volume, do you remember the formula? M rho Vg equals the weight. Do you remember this formula? We did this in hydrostatics. Now, what's the formula for weight? Come on, mg. So what's the formula for mass? Mass is density multiplied volume. Okay. So here I have the mass.
Density equal m over
Yeah. So density. Yeah. If you want to say it that way too, density equals m over v. So my density is 9. Did I say 9? Yeah. 9 grams per centimeter cubed. That's to equal the mass, which is 64 grams over the volume.
So 64 over 9.
Yeah, so calculate that, please.
We should change the unit to cm.
Yeah, these will all, no, just leave them as cm. Yeah, this is cm.
7.1.
So volume equals 7.1
Oh,
cm cubed.
yeah.
Yes? Yes, yes. Okay. Now that's the volume for one, or 64 grams of it. Okay, but we just want it for one. So what we have here is, how many atoms do I have in total?
6.02.
6.02 times 10 to the 23 inside 7.1 centimeter cubed. So now, Jingdong, I need to, I just want to get one here. So I say one atom has volume 7.1 over, or maybe Mustafa, 6.02 times 10 to the 23.
1.17900.
1.17 is fine. Times
10, 23.
minus.
No, positive 23.
No. It should be minus, right, guys? Look here, Jing
Yeah,
Dong.
minus, yeah. It is minus 29. Yeah, minus
Centimeter cubed. Yes? Now, what shape is an atom? What shape is an atom? A sphere, like this, yes? So here is or. So what's the formula for volume of a sphere? 4 over 3 pi r cubed equals 1.17 times 10 to the minus 23. So then I get r cubed equals 3 over 4 times 1.17 over pi times 10 to the minus 23. Can you calculate, please? So, I mean, it should be about 0.25. Yes? Yeah, go ahead.
2.8.
Hang on a second. Just be careful here, okay? What is it?
2.8.
10 to the minus 22?
Why cube? Because centimeter cube?
That's the formula for volume of a sphere. Yes. You're going to die. Alright, fine.
2.5.
Thank you.
70.
Wait, 2.57 times 10.
24. Minus 24.
Okay. 2.579. So 2.8. Okay, right. So now I do cube root. So I get, can you do cube root of 2.8, please?
1.4 times 10 minus 8.
That's centimeters, yes? So in meters, 10 to the minus 10. Yes, did I do that right? Or do I have it the wrong way around?
That's right.
1 minus 3
Yeah.
divided by 3. Is this 0?
Wait. Or if you want, that's or equals, I think how they write it in the book, is 0.4 times 10 to the minus 9 meters. And the reason for this is because this is actually, this is a nanometer.
Okay, why you divide by 3, 24 by 3?
Huh? Oh, because it's taking cube root. The fourth rule of powers that we did in maths class. Cube root is power 1 over 3. So you can see, anyways, my point is the constant. What's the constant called? Yeah, it's very useful constant. Okay. Now, so we've done, well, we haven't, but in Rain's class you did Ionic Bond, Covalent Bond, and Metallic Bond. Yes? And Van der Waals Bond. Or not? You've done all of them? Good. Good. So, one of you can give me the definition of Ionic Bond.
Ionic bond?
Yeah.
It's the bond between
Metals
metals
and non-metal. It's going to be gains.
And what causes the bond to hold together? What's the...
it's the negative and
Yeah, a negative and a positive, yeah?
And something like
No, just don't, I don't need fancy words, just give me the informal, whatever way you want to explain it.
alright. So different charges.
Different charges, yeah. Ionic bond, you have like positive charge and then negative charge, yes? And then they're together, yes? Okay, no, that's good, Hussein. Ted, can you give me covalent bond? Can you give it, Jingdong? You give me the definition of it.
Each molecule, each atom provide one electron.
Say that again. You said that too fast.
Each atom provide one electrons.
Yeah, what word am I looking for? You said paired?
Mostly between non-metals.
Come on, somebody.
Shares
Thank you, Ted. Shares an electron. Thank you.
Yes, I mean this.
Yeah, I was listening for the word share. I didn't hear share. Did you say share?
No, I said each atom provide one.
Paired.
Provide.
Huh? What word are you telling me?
Providing.
Oh yes,
No. Shared. Shared. Very good. Thank you, Ted. Metallic bond.
Swimming around the metal, around the what?
No,
Metals.
protons swimming around the in an electron sea. That's what they said.
Yeah.
Yeah.
Metal atoms having one or two outer electrons that are generally loosely held and are easily lost. So basically, like they have here the picture of the metal, and the electrons, they're very loose, they can easily fall off. Yes?
Yeah.
Okay. And then the last one, now did you do this with Lorraine? Van der Waals bond.
Yes.
Alright.
Long dispersion forces. Yeah.
What is it?
Bond and dispersion forces, yeah.
Yeah, what is it?
It's the bond type.
Yeah, it's a weak bond between atoms.
Yeah, but what causes the bonding?
Covalent bonds. Again, negative charge. I mean, it's a result of negative charge, but it's the weakest type of bond.
Weakest type of bond, yeah.
Yeah.
So you have Van der Waals force are very weak and they're present in all atoms and molecules. They arise because although the centres of negative and positive charge in an atom coincide over a period of time, they do not coincide at any instant. There is a little more of the electron cloud on one side of the nucleus than on the other. A weak electric dipole is produced, giving rise to an attractive force between opposite atoms of such dipoles in neighbouring atoms. So I'll try and draw you a picture. So, okay, I apologise if this isn't 100% chemically correct. You can ask Lorraine for it, okay? So here's your hydrogen, and here is proton, and here is electron. Yes? This is positive charge, and this is negative charge. And this one here is proton, and this is positive, and then this here is negative. So what's the total charge here? 0. And what's the total charge here? 0. So will there be any bonding between them? No. But if you draw them side by side like this, proton, electron, and then proton and electron. And let's say it's going around like this, and this one's also going around as well like this. Whoops. Did I draw that right clockwise? Yeah. When the electrons are here and here, there's negative and negative, and although these cancel because these are close together, what happens? They come closer or further apart? Further. So this gets pushed this way and this one gets pushed this way. But then when this is around here and then this one is around here,
They also repel each other.
then they also repel. Okay? But maybe, for example, if this was here and this one was here, what would happen? They attract. So in total, the force is 0. But it kind of changes. Sometimes, it moves a little bit. So, let's try and tie our words in earlier. So this one, does it stay still? Does it stay still? Not really, because at the beginning maybe it moves to the left, and then maybe to the right, and maybe it goes up, it goes down. It kind of goes like this, yes?
Yeah.
Right? Because it's not always balanced.
Brownian Movement.
Thank you. And so it makes Brownian motion. So Brownian motion, or Van der Waals bonding can cause Brownian motion. Yes, come on in, Leslie. Okay. Happy?
Yeah.
Sorry.
Okay. Fine. Continuing, so. Now, Ted,
Yes.
give me your definition of van der Waals bonding. Yes, the one I just did.
So weak
Yeah, go on.
weak
Yes, yes.
I can help him. Okay.
You can't help him. You were in the bathroom when I was giving the definition.
But Dr. Lord have told me yeah.
She told you van der Waals bonding?
Yeah.
Go ahead.
For example, if we write on the paper,
Yes,
because of the vulnerable is very weak,
yes,
so that we can, so that the ink
yes.
can be
Yes, yes. I remember this. I was in the office when she was teaching you this.
yeah, yeah.
But I want the explanation that I gave on the graph. Albert, can you give it to me? You're writing notes, yes? And you really need to be writing notes all the time. Go ahead, Albert.
Temporary dipole connected.
Yeah, but what causes it?
When the electrons are positioned
Yeah, the position of the electrons.
Yes.
No, I don't want this.
I want them to look at it.
No, later. Ah, please, everybody, while I'm teaching, you need to be making notes. Yes? Yes?
Yes.
Thank you. All right. Now, what I want to do with you now, kinetic theory, or kinetic model, actually. Model. Okay. So here's our container. Yes? And it's a gas. And we'll talk more in a moment about gases and solids and liquids. But we know from chemistry, here's our gas. And these all move, yes?
Yeah.
Now what happens when it comes against the wall? It bounces and comes off like this. Yes?
Yeah.
Now let's say this momentum is mu and this momentum is mv.
Why is this MU and that's MV?
Well, this is before and then this is after. Okay? So what's the change in momentum? That's going to be mv minus mu. What's the formula? Over, oh sorry, that's just the change in momentum.
It's delta P, yeah? Change in momentum.
Change in momentum. Now, do you have some rule about momentum from Newton? Do you have some rule about momentum from Newton? So, conservation of momentum is one. What's the definition of force?
Oh, you mean the force and reaction? Do you mean this one?
Not this one, no.
No, not that one.
Not this one. Huh? Yeah, what's this? Yeah, which is what? What's I called? Impulse. Oh my goodness. Okay, hang on. Let me draw you a bigger picture now. Right, here's the wall. Here's the particle. Its mass is mu. It's momentum. It comes in and comes back out, and its mass now is mv. Yes?
Yeah.
Okay. Now the change in momentum is this. mv minus mu. That's the impulse, the change in momentum.
Delta P.
Delta P if you want, yes. Delta P. Now if I divide both sides by T, delta T, I get this. T. Or delta T, it doesn't matter. But this equals mv minus u over t. And what's v minus u over t? A. So it equals ma, which equals f. Yes?
Yeah.
Good. Now, so we have this formula that m v minus u over t equals f. Yes, okay?
Yeah.
Good. Now, from formulas we did in hydrostatics, what is a formula that uses force? Force. No? In hydrostatics. Remember, pressure
Minus K.
equals force over
Yes.
area. So we could also have force equals pressure by area.
You mean stress?
You like stress, pressure. So I can say that m v minus u over t equals PA. Yes. Okay. So you could have m, or actually, I'm just going to write delta P now. Delta P over delta T equals P times A. Is that okay? Good, alright. Now, I need to go to the next page.
Wait.
Delta P means momentum.
Change in momentum, the MV minus the MU.
Please ask.
Huh?
That's fine.
And P here is, big P is pressure, sorry Albert.
Okay.
That's small p, okay? Now, you can say delta P equals P times delta T, and I can divide by the area here. Yes? So you have a formula here. This is the change in momentum per unit area equals pressure multiplied by the time. The delta T. And then if I divide by the delta T, I could get something like pressure equals the change in momentum, change in momentum per unit area per unit time. The whole reason I'm doing this is so in your head you can think of pressure as being high pressure means the momentum changes a lot per second per area. Okay?
Yeah.
It's another way to think about pressure. You can think about pressure as the change in momentum when the particles hit the wall. So if I make the particles hit the wall faster, is that more or less pressure?
More.
More.
More, yeah.
If I make the particles move slower, less.
Less pressure.
Yes?
Yeah.
So if I make the area smaller, what happens to the pressure?
Make the error smaller.
Yeah.
More.
More. Yeah. So like here maybe is my gas, okay, and it's going into a bottle. If I make this area smaller,
The pressure will be bigger.
pressure will be bigger. And if I make the gas go faster,
The pressure will be bigger.
pressure will be bigger. So pressure, another way to think about it is the change in momentum per unit area per unit time. That's another way to think about it. And that is called the kinetic model for pressure or for gas.
Also, temperature affects this.
Temperature too, yes, exactly. And we're going to connect this with temperature later. In fact, we'll see that temperature is actually a measure of the energy per particle in motion. But all this will be connected later. But just for the moment, I want to introduce this idea for you to think of a new way about pressure.
Will we be doing the experiment for this one?
No, I don't think so.
What is it?
Yes?
Can you go back to the last page, please?
Last year we did on the computer. That we did the
Computer simulation.
yeah.
That's cool. Let's see if I can find an app online for it.
No,
Unit
it's-
10.
Unit time.
Okay.
Okay.
And moment, M-O-M-E.
Momentum. You know
M-O-M.
momentum? M-O-M-E-N-T-U-M.
T-U-M, not,
Yes.
not A-M.
Not AM, sorry. It's mass multiplied velocity. Yes?
So in physics we also use van der Waals forces.
No. You just need to know what it is. Just the definition. For the moment. Don't worry.
But in chemistry,
Chemistry should be much more important to
say
you.
we use London dispersion and not van der Waals is the same.
What is?
London dispersion forces.
No, I can't hear this word. What?
Yeah, they are same.
What's the same?
London's first post with the Van der.
No, I'm just going to use van der Waals.
The same thing.
Are you asking me something or telling me something?
I'm asking.
So what is your question? And do you know the answer to it?
I'm trying to understand.
Yeah, go ahead, Albert.
London dispersion forces.
I don't understand this word.
Oh, it's okay. He's saying the other name of
This
the
is the same.
VDW.
Yeah.
Van der Waals.
Yeah, its other name is London Dispersion Forces.
Okay, if that's the other name for it, congratulations.
Yeah,
But I'm not going to use this name.
In physics it's not like.
No, for physics, I'm just going to use van der Waals. I will not use anything else. I will not make my life more difficult. Okay. So, we're going to look at the 3 states of matter. And we'll look at our, for example, ice.
Solid, liquid, gas.
Very good. Water.
Liquid.
And then,
Gas.
Gas.
It's the same question.
oh, how could you have a question
No.
already?
No, when
Is it related to this? Because I'm so tight on time.
No.
No, so you can ask me later. Gas. Or evaporated, or steam, sorry, steam. I forgot the word for steam. Steam. Okay. So we have ice, water, and steam. As a good example of the 3 different states of matter. So you have ices. Do we know the name for ice? What type of state it is?
Solid.
It's a solid, yeah. And water,
Liquid.
and a steam,
Gas.
gas. They're the 3 states. So ice melts into water and then it turns into
Yes.
gas. Please write these words down, please, please, please.
Should we remember all of the directions, definitions?
Yes.
We will be asked.
Yes.
Exam.
Yes.
And for the next, for the second semester final exam will be on this also?
Will this be on what?
In the second semester final exam?
Yes. Everything is in the second semester final exam.
The final exam is not easy.
No.
But last year.
Nobody told you it'd be easy.
No, last year the exam was easy.
No, maybe this year it won't be.
Yeah, well, it was probably the easiest.
Okay. So, what's the difference between solid, liquid, and gas?
The particles
Yeah.
tightness.
Yeah, tightness is fine. So, when you picture a solid, what way are you picturing the particles?
Close to each other.
So what, like something like this, yeah?
Yes.
And then when you're picturing water,
A little far.
maybe it's moving a little bit, yeah? Yes. And then for gas,
No control.
Crazy.
Increase.
yes? So, the difference between each state is a difference in how strong the bonding is, yes?
Yeah.
So in solid, strong, medium or weak?
Yeah.
Strong,
Medium.
medium
Medium.
and weak. So all you need to know is that it's the bonding. Did you do this with Lorraine?
Yeah.
Yeah, good, okay. So we won't spend time on it. Okay. Right, let's see. We already talked about grain boundaries. Jingdong drew us the diagram for grain boundaries. And in fact, if you look at page 19, here's the picture of it. You see it? This one, yeah. You see it? Yes? You see it? So that is grain boundaries. It makes it stronger because it's all different shapes stuck together.
It's a branch. It's a branch.
Yeah, yeah. Good, okay. Right. Do I want to talk about the crystal structures? Oh, a little bit. Okay. So if you look now, we have face-centered cubic. So this is how they're put together. So if you look at the diagram on page 20, they give you a little diagram here. So you have one here, 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 and here. And then you also have one here, 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 and here.
And the crystal.
That's what's called face-centered cubic. It's how they're stacked together. And then there's another pattern called hexagonal close packing. Hexagonal close packing.
That's
So-
the same name?
You can see the diagram here. It's when it's like this. Oh my goodness. So you have atom here, 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 and here, and then some here. And then you have 3 in the middle. That one's called hexagonal. And then the last one we have is body centered cubic. So that's when they're packed like this.
We have to memorize the draw also.
Yes. Sorry, this isn't great. So that's when you have 1 in the middle, and then 8 here, 4 there, and then 4 there. So you have 9 in total. So if you look at the picture, it looks like this. There's 4 stuck here together, and then there's 1 in the middle, and then there's 4 at the bottom. Oh, that's terrible. You can see it there. Okay. Oh, do we need to do the last one? No, I don't think so. The first 3 are most important. So you have face-centered cubic, hexagonal close packing, and body-centered cubic. And it's just different ways that they're stuck together. But they're very, very close together. So what do we think? Is it for solid, liquid, or gas?
Solid.
Yeah, these are all solids.
Close.
Yeah, they're very packed together. Okay. So he gives you some pictures here. See here? So this is a bubble raft. Do you know soap bubbles?
Soap bubble.
Yeah.
What's bubble?
Oh, somebody
oh,
tell.
I know.
Do you? What's a bubble? Tell me.
Just like ball.
Yeah, like a ball, yeah.
The sheep.
Yeah. You wash your hands and you make bubbles, yeah? Yes. You know bubble? Good, okay. So here's a picture here. And you see the bubbles for soap. You see they're all neat. You see here? It's a nice order.
This is solid.
Yeah, well, no. Firstly, I'm just saying they're all nicely lined up.
Okay.
It's very nice order to them, yeah? Okay. So what type of shape are these? What type of bonding or pattern are they? Let's see. Figure 2 point is in, yeah. Now it's so difficult to see, but they're hexagonal. Hexagonal. Do you see hexagonal?
Yeah.
If I try to show you here, look, it's really difficult to see, but they kind of make the hexagon shape, the 6 sides. Maybe I'll have to show you. It's how you look at it with your eyes. So like, yeah, if you take one for the moment, like look here, you see that, if you look at what's around it, yeah, you see it's a hexagonal. It's this one, hexagonal. So this pattern is hexagonal close packing. Yeah? Can you see it? So like if you take one, for example, look at what's around it. It's a hexagonal shape. Can you see that?
No.
If you look at one and look at the particles around it, yeah, it's this shape here, hexagonal. Yes, can you see that, Leslie? Xingdong?
Should be or C.
This one. If I take one here, and if you look at what's around it,
Oh yeah, I saw.
it's this one. So this is example of hexagonal close packing. Yes? Do you see that, Leslie?
Yeah.
Here, Xingdong, you can show them there.
Like a beatbox.
Huh?
Like a beatbox.
I guess so. I don't know. I don't know the shape of it. Here, he'll show you. Okay, are we happy with that? So, if you want an example of this one, here's a picture of it, okay? Alright. Okay. Next page, please. Okay. So, before the discovery that enabled the arrangements of atoms in a crystal to be determined experimentally, crystallographers had simply assumed that the regular external shapes of crystals were due to the atoms being arranged in regular repeating patterns. In 1912, 3 German physicists, Max von Laue, Frederick and Kipping, found that a beam of X-rays on passing through a crystal formed a pattern of spots on a photographic plate. Shortly afterwards, they showed that this pattern could be used to reveal the position of atoms in a crystal. Together they proceeded to unravel the atomic structure of many substances and started the science of X-ray crystallography, the structure of many complex organic molecules, including like DNA, for example. So what's he saying here is, now we haven't done this yet, and it's a pity it's near the start of the book. X-rays, you know X-rays? Like when you go to the hospital.
Yeah.
Has anybody got this?
Bone break.
Bones break, yeah.
Yeah.
A crystal has this very nice shape to it. Something like this, okay? Well, that's not nice. Like this. Okay. And then you send an X-ray in. So here comes the X-ray. And what happens is it comes out, it bounces out, and it hits, you know, a plate. And you get the picture here. What these scientists did is, by looking at this picture, they were able to work out the shape here. So they were able to go backwards. So they looked at the picture, they looked at what they got, and they said, okay, so it must be like this. And they were able to, you know, get information about the size and the distance and everything. So they can use this technique to get us information about atoms. Okay? And if you look here, here is examples of different X-rays. You see here? So this one here and this one here are two examples.
What's polycrystal?
Yeah, well, we'll look at that now. Okay, so where will we continue? Oops. Okay, so what's happened here is, I'm trying to see, yes. In figure 2.19, where's that? Yeah, in figure 2.19, a polycrystalline sample, many planes are involved at once and thousands of spots are produced, resulting in circles. Figure 2.20 is due to polycrystalline sample, and 2.20b to a single crystal of the same material. So what's happened there, Mustafa, is the first one is when you have something, I'll try and draw it for you, okay? You have many layers. And then the second one is just one layer. So what happens is when the X-ray comes in, it has lots and lots of things it can bounce off of. And that's why you get this very bright picture.
Why can you say it again?
Yeah, because there's so many things to bounce off, the hit, it makes this really bright picture. Like for example, maybe the X-ray bounces off this one, and then maybe it bounces off the one behind it, and they go to nearly the same place on the paper. It makes it very bright. But when you have it like this, the X-ray comes in, bounces off this, the X-ray comes in, bounces off this, you know, they're far apart. So you see this bright one here is because it's very high density. There's lots of particles. Whereas this one is very light. That's why there's lots, you see there's lots of black space. Yes?
Mr. Steve,
Yes.
this picture, this picture means that because of the atom structure different.
Yeah, because the structure, yeah.
Different. So the energy which come, some of the energy can be reflected.
Perfect, yes.
So we can show it brightly.
Yes. The bright one means there's lots of energy reflected onto the plate, yes. And then the black one means there's not much energy reflected. So like if you take an extreme example, if I only had one molecule or one particle, the X-ray comes in and just makes one dot. But if I have a couple, it comes in and maybe makes 4 dots.
Okay,
So
if it have a shape like a cube.
And then it'd be brighter. Now if I had some more behind them,
So it will be more dots.
more dots. And when there's more dots together, it looks bright.
Okay, it will be together in the same point if they have a shape, right?
Hmm?
They were gonna fill in the same point if they have a shape.
What do you mean?
The first thing you draw it with the cube.
With the cube?
Yeah, why is it's filled in the same point?
I don't understand what you mean.
No, it's two is
Go down?
No, no.
Oh,
The same one, yeah.
here, this
Yeah,
one.
Same one, yeah.
Yeah?
Let's fill them in that point, right? And just in one dot.
This one here,
Yeah.
one dot, because the two are close together, that maybe they almost make the same spot on the paper, and it makes it look brighter.
Because they are close together.
Yeah, because they're tightly packed. Like if we go back to our shapes, like, yeah, I'll give you a good example. Can you go back to page 20? And you see hexagonal close packing. 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, and then there's 3 in the middle. Okay, you have this one. And then let's then do body center cubic.
That 8 for above.
How many do you have? 4 above,
4 below.
4 below,
1
and 1 in the middle.
Yeah.
I think if I sent an X-ray on this,
Yes,
yeah, it will hit off these 4,
Yeah,
but there's
it's
only
the
1
same
in the
one.
middle.
Yeah.
So maybe the graph would look something like this. You might have bright here because of the 4 on the top,
Yeah.
and then you might have bright here because of the 4 on the bottom, and then there might just be a dot in the middle.
Yeah. That puts it into this one, hexagonal.
I think in this one here,
You're
it'll
gonna be
be
the opposite.
very bright on the top and the bottom
No.
because you have lots on the top and the bottom.
Okay.
And then you have 3 in the middle. So I think it'd be brighter in the middle.
So you mean the hexagonal close packing is better than body?
Well, not that it's better, it just makes it brighter because there's more, it's more packed in, you know. And then what's the other one then? And then face center cubic.
It's
Yeah,
gonna
I
be
think,
more brighter.
I think that because there's 4 in the middle.
Yeah, a lot of.
Yeah, so you can see how the X-ray can tell us more about the structure, the shape. Yeah?
And Mr. Steven,
Yeah.
if it is more brilliant, that means the atoms get closer, or
Yeah, I think there's more atoms closer to reflect.
okay.
Black means, if it's black, it means nothing hit the paper here. So for this one, I think the X-ray comes in
Black.
and hits there, and hits there, and then in the middle, but then there's nothing here. So that's why there's nothing like here and here. It's black then. Yeah? Okay. Not quite. There's just one thing to do at the last thing. Come on, wake up, man.
Thanks, Mustafa.
I'm not. Well, I could tell you were asleep. You're sitting right in front of me.
No logic in this, that's why.
Polymers. What is it? Well, have you done polymers with Lorraine?
No, but in biology,
You did it in biology.
yes, polymer.
Jing Dong, go ahead and give the class the definition of a polymer.
Polymer.
Yes. Listen carefully to it.
Let me think.
Go ahead. Take your time.
Polymers means there are many small atoms that get together to form polymers.
Yes. Can you give me an example of one?
Polypeptides.
Okay. This is a biology one, yeah?
Yeah.
Okay. So that's an organic one. Right. You basically got the key thing right at the start. So a polymer is when you have lots and lots and lots of atoms together to form one molecule.
Yeah.
Can you all give me an example of a molecule? Give me a very simple molecule. H2O, right? H2O. What is H2O? Yeah, but what is it made of?
H and
How many hydrogen? Two. And oxygen? One. So how many atoms in one?
3.
3 atoms.
And
Okay.
CH4.
Let's just do H2O.
Okay.
Or why not H2SO4? Why not? We pick many, many examples. But the number is going to be small, right? But a polymer is when you could have like 1,000 atoms together. Or maybe even more. Or yeah, 100,000 maybe even. So polymer is when you have lots and lots and lots and lots of atoms together to make one molecule. Now what do you think the if you're interested in polymers, what do you think is useful about polymers? Ted, can you think of anything useful about having so many atoms together? No. Any ideas?
What's the question?
Something useful about having so many atoms together.
Genus?
Stronger? How? Why? Yeah, well, why would it be stronger? Well,
Maybe more brightness?
yeah, if you have hundreds of thousands
Gonna be more brightness.
together, there's going to be more bonds, yeah?
Yeah.
It's going to be very strong.
Yeah.
Lots of bonds. So, a polymer, it can be very strong. Now, Jingdong said he did this in biology. What's it useful for in biology?
That thing is useful. It just told us what's the polymer.
Okay, well, I'll tell you, look. If you look here, for example, I think it doesn't say it here. Yeah. If you take a tree, for example, okay, here's your person. Now, this person, he's doesn't fall apart because of his bones, yes? You all know bones? Yes? Keeps them together. But take a tree, for example. Does a tree have any bones? No. But it doesn't fall apart. Why not? Because it's... I'm drawing this badly. You know what this is? Cell? It's inside this person and inside this? The cell? This cell is different in the tree than in the man. What's different about it?
There's blood in there.
Yeah, but what's different about the cell? Yeah. In this one here,
There's a wall.
There's no wall. Cell wall.
which one has the wall and which one has no wall?
Tree has
Tree has
tree has a wall and it's like a proper shape, but human and animal cell is like there's no protection.
Very good. The tree has a cell that's very strong like this, whereas the human,
And
not so strong, right? Maybe like this, I don't know. Anyways, this here is actually a polymer. It's lots of atoms put together to make it really strong. Because this tree has no bones, so it needs the cells to provide strength for it. So a good example of a polymer is in a tree, in the cell, gives it more strength. This is where you could see a polymer in day-to-day life. Okay? Another example of a polymer, I think, is, do you know nylon? Yes?
I know an example of polymers.
Go ahead.
The polymer substance such as used for suspension, SUSPENSION.
Suspension.
Yes, it's usually used in liquid, such as this kind of
Paint.
Oh yes, it also included polymers.
Okay, so you're telling me that inside paint there's polymers.
Oh yes.
Okay, I didn't know that. So I guess you put polymers inside the paint.
Can I do the black?
No, you can tell me. You can use your English. I know you like to practice your English.
Such as there are couple of liquid.
Yeah.
And there are some small particles.
Yes.
If there is no polymers suspension,
Yes.
the small particles will fall down the bottom. If there are polymer
Suspension.
the particles will leave.
So you're telling me that for paint,
Yes, not just for paint.
but for example, for
Yeah,
paint,
yeah.
they include polymer to stop the small particles falling to the bottom?
Yes, to let the small particles arrange very.
And what would be, Jingdong, what would be the problem with paint if you let the small particles fall to the bottom? What would happen?
Be more solid probably maybe.
Yeah, would it mean that the paint, like if the small particles fall to the bottom?
As you see the colors, these yellow colors, they are all small, very very small particles. If the particles fall down.
So I
bottom.
understand.
Yeah.
So you're telling me for paint,
Yeah.
the color comes from the small particles.
Yeah. Yeah.
And if the small particles fall to the bottom,
Yeah.
it means your paint changes color.
Yeah. Yeah.
So you put in the polymers to keep the small particles
Arrange balance.
arrange a balance. Very interesting. Thank you, Jingdong. Well, there you go. I didn't know that. So for paint, the color comes from the small particles, and you put in the big particles, which are called polymers, to stop the small particles from sinking to the bottom. So that's good. Do you have any other examples of polymers? Paint is good. Anything else? And I think we did the tree as an example. Plants. Nylon. That's what I was doing. Nylon. Do you all know nylon?
Yeah.
What's nylon, Jingdong?
It's a substance that can be used to make bag.
No. Give me a more day-to-day example of nylon. I'm saying, do you know what nylon can be used for?
It's not kind of nylon, this chair.
No. Come on, day-to-day life.
To protect the food for
No. More day-to-day than that.
Nylon.
Nylon. You ever hear of nylon tights?
Refrigerator and airplane.
Can be used to making lime.
You all have mothers, right?
Mm.
Yes? And your mother wears tights, maybe?
Yeah.
You know what I'm talking about? And it's stretchy. It's black.
The tie.
The tights. Do you know this?
Yeah.
I hope
And
so.
some plastics bag.
I know, but I'm just talking about this first. Do you all know this?
Yes.
This is made out of nylon. Nylon is a polymer. It's very strong,
Okay,
Yeah.
I understand.
but it's very, very light,
Yeah.
but very, very strong.
Yeah.
Yes. Yes?
Nylon can also used to be made the thing when we go to sleep.
Go to sleep.
Yeah.
Oh, I understand what you mean. Okay, yeah.
How is that in English?
Are you sure there's nylon in that? The blanket.
Yeah, the blanket. Some maybe.
Some maybe have nylon in them. Yeah. Okay.
The skin of the blanket.
The skin. Okay. Yeah. Okay. Maybe so. Maybe so. I don't know. I don't know what's inside my blanket. I don't check the tag, the details. But you're saying that you could have nylon inside blankets.
Yeah.
Okay, fair enough. Why would you put nylon inside blankets?
To protect. Protect.
Protect?
Yeah, protect.
Yeah, I think that'd be a good reason. So it doesn't tear, maybe.
Yeah.
Yeah, I think you can have nylon in clothes too, can't you?
Yeah, clothes.
I don't know. Do you have a tag? Yeah, take your jacket off. Albert, let's have a look. If there's any nylon inside it. Yeah.
In Chinese we say nylon.
Nylon?
Yeah.
Okay. In Ireland we say nylon.
Nylon.
Yeah, in Turkey we say nylon as well.
No, not this tag. The tag with what's here, this tag. The outside. This part here is 100% nylon. See? 100% nylon.
So the example is actually near us.
The example is very near us. So this is nylon. Okay. Yes? Now you can look, you can see the difference, okay? This here is very soft and very thick. Where if you look at the outside one, it's very strong,
Yeah.
but very light.
Yeah.
It protects, like what you were saying, Leslie. The nylon protects the inside.
And
Yeah.
that very quickly.
So nylon is a strong polymer. Yes?
Yeah.
Do you have one? What's,
No,
no, I don't think so because it's
Yes.
soft, yeah?
That's for me. Mine.
Yeah, maybe your one.
Yeah.
Here.
Chinese.
That's not good to me. Alright, well anyways, that's a polymer. Do you all know what a polymer is now?
Yeah.
So Ted, what's a polymer? Shh. Come on, Ted's explaining polymer.
Okay.
Go ahead, Ted.
It includes giant micro,
Yes?
macromolecular.
Yeah, so polymer is a giant molecule and has many, many atoms. Yes? Okay, go again. Go ahead.
Has many atoms.
Yeah, go on. Give me a full sentence. Don't be shy.
Talk faster, goddammit. Just kidding.
Leslie, come on. You're distracting Ted. Go ahead, Ted. A polymer is,
Polymer is
you were right, a giant,
a giant molecule.
yes? Go on.
With many atoms.
Perfect. You need to be more confident.
I need to be more academic.
No, more confident. More confident. Okay, we all know polymer now? Okay, so you have 5 minutes left. I want you to try the questions, please. I'm sorry. I'm sorry. This class, 1, 2, 3, 4, 5. I don't want to see 6 boys. I want to see 6 men. So no complaining about the work.
What's the
I'm not
question?
saying anything.
The question is, do the questions in the book. Here they are here if you don't have your book. No, don't worry, Ted. I have them right here for you.
No calculation.
Oh, calculation, vocabulary, everything. It's in the book, but here's a copy of it anyways.
Mr. Stephen, can you go back to the calculation of atom?
Can we open the windows?
Yeah, go ahead. Let me just stop recording here.